Hi students, welcome back to geology. In this next video, we're going to move on from volcanoes specifically and look at other ways that igneous rocks can form. So we're looking at plutons and igneous rock bodies. What happens when magma never erupts out of a volcano? So first things first, our pondering question. What happens when magma never reaches the surface and it just stays internal? So this is what we call a pluton. So below a volcano, the Pluton or a batholith. So this is a frozen magma chamber. When magma never actually erupts out of a volcano and it cools slowly underground, we call this a pluton. And this is an individual pocket of magma. If we have a large deposit of this, we call this a batholith. Okay, so you can see the magma chamber trying to upwell. It doesn't ever make it to the surface. Maybe some of it makes it to the surface, but not all of it. And eventually it freezes. Well, it doesn't freeze. It cools and solidifies. And then it's basically this frozen in time magma chamber that creates our larger grained, larger crystals in our igneous rocks. So we call these intrusive igneous rocks that our plutons create. So as I mentioned, plutons are a single eruption or intrusion, and then batholiths are groupings of these intrusions. So several of these plutons put together over a large area. So large batholiths will lie under ancient volcanic fields. So for example, in the Sierra Nevada, we have the Sierra Nevada batholith. And prior to all of those plutons coming to the surface from uplift and erosion, it was a large volcanic field from the subduction off the coast of California. So that used to be a bunch of volcanoes, and now it was leftover magma chambers that solidified and then came to the surface from uplift and erosion. So here's a look at from the east side of the Sierra Nevada. This is Mount Whitney, which stands at 14,505 feet, which is the tallest mountain in the contiguous United States, which does not include Alaska, Hawaii, and other U.S. territories. So this is just in the 50 states that are connected. So this is part of the batholith. And again, this is when a large body of magma cools inside the crust and a massive rock forms and then is exhumed at the surface so we can actually see it. Within these plutonic rocks, we can see things like magmatic domes, which are smaller bodies of hardened magma that can form into these kind of dome features. And then as it's uplifted and eroded around it, the dome is at the surface and you can see it. When erosion starts to take place, sometimes the domes no longer look like they did when they first formed. And Half Dome is a great example of this, where it lost half of its dome from glacial and landslide erosion. Additionally, we have things called laccoliths, which are kind of like blisters in the crust. They are intrusions of magma that form between sedimentary layers. So magma is trying to come to the surface and it kind of bulges upwards and outwards, and it creates this intrusion. And then when it solidifies, we call it a laccolith. Other random things that can happen are like dikes. This is when random magma will intrude in a crack or a fissure, some sort of fracture in the rock, and it kind of cuts across the rock that's pre-existing. And then they solidify in place. So those white lines that are running through the rock there, we call those dikes. So they cross other rocks that existed. And then they also help us for dating sequences, knowing that that rock, because it cut through other rocks, is younger than the rock that it cut through. And that'll make more sense when we start talking about geologic time and putting things in order chronologically. Sills are similar to dikes, but they form horizontally instead of vertically and at an angle. And so sills intrude between sedimentary layers and then crystallize in place. This generally is when magma just is seeping through weakened layers. And then again, it will solidify in place. So there's an example of a basalt sill that has solidified between two sedimentary layers. Other things that can happen are like fissures. So when there's some sort of crack in the rock, this or the crust, this can happen from faults that have moved and other just weakened rock. The magma can intrude into those and then come out of the crack at the surface. And so these oftentimes are found like on the flanks of shield volcanoes, or maybe where we have some transform movement and additional magma in the region, which is not always common, but it can happen. So fissure eruptions are mainly formed from basalt, or mainly form basalt. Lava tubes are another really interesting feature. This is basically a conduit of where lava was flowing. So as lava was flowing underground, or even above ground, it can create this tunnel as things on the outside crystallize and solidify. And as that happens, it insulates the lava. And so the insulated lava ends up really hot, very low viscosity, and can flow really quickly. And when the lava shuts off, so there's no lava feeding these tubes anymore, we get caves like you see in the right-hand side there, and we call them lava tubes. Other features are volcanic necks, stalks, and plugs. So nothing erupted here, but the magma chamber basically solidified, and then things around it eroded. And so it's a remnant core of an ancient volcano. We have Morro Rock as an example, and then we have Devil's Tower and Shipwreck are necks. Morro Rock is a plug. And Morro Rock is actually part of a series of other plugs. So an example, this is our example, one of our examples in California anyway, of volcanic plugs. The Coast Ranges have what we call Morro Rock and the Nine Sisters, which is formed from decompression melting. Okay, so we used to have a divergent plate boundary between the Farallon Plate and the Pacific Plate. The Farallon Plate was converging with North America, and as that happened, it brought that divergent plate boundary to California. And then as it hit the coast of California, it caused decompression melting, which allowed for volcanism to happen. And there's this line of volcanoes or remnant volcanic plugs going from east to west. And then there's a couple of off the coast that are underwater as well. But the ones that you can see are Morro Rock and the Nine Sisters, and they're all a series of volcanic plugs that are from the decompression melting. Another interesting feature we can get is columnar jointing. This is when we see fractures as a result of the cooling process. This happens very often with basalt. And they form outside and then towards the center. So there's shrinking that happens as things cool, and it forms this really interesting hexagonal pattern. And so it kind of looks like tiles that somebody has laid out. But again, this is formed naturally. This is not man-made. So other than the background photo, the other three in circles are examples from Devil's Postpile, which is near Mammoth Lakes on the east side of the Sierra Nevada. Another example that's a little bit closer is Table Mountain. Table Mountain has 10 to 12 million year old columnar basalt. But the other thing that's really cool about it is it also has inverted topography. What inverted topography is what's on the top of that mountain used to be the bottom, the low elevation. So what happened was this area used to be, the top of this mountain used to be the bottom of a river channel, which was the old San Joaquin River channel. And around it used to be granitic rock, okay? When a lava flow occurred, which geologists do not actually know where the lava came from, they think it's probably from Nevada, but it's kind of a question mark. It flowed down the San Joaquin River channel and it solidified there. And when it solidified, it capped that river channel. And basalt is not as erodible as the gravels and the granitic rock around it. And so the basalt left a flat table that capped where that ancient river channel was, and then everything around it eroded. And so while it is now the high point in the topography, it used to be the low point. So we call that inverted topography, which is a really interesting feature to have right in our backyard. All right, some final thoughts here. Plutonic rocks form from these plutons deep underground. We crystallize magma chambers, and then we end up with these really large crystalled rocks. All of our volcanic rocks, which we'll talk about in the next video more in depth, we'll talk about rocks. Those form much smaller crystalled rocks. Okay, a group of plutons is known as a batholith. Plutons can form domes, and then we have other features that we talked about. We talked about volcanic necks, sills, dikes, laccoliths, columnar jointing, all of that good stuff. In your notes, I want you to explain how and why crystals grow large underground and what might be required in order for them to do so. I'll see you guys in the next video. Bye.